Okay, so about the data processing of this RNN, so we use the data set of Bach solo cello. So it will basically be either monophonic or polyphonic, or not polyphonic, but homophonic, right? So therefore, even if we have something as the chord, right? Like as I what I showed yesterday, like something like this, but you can still distinguish the mean melody there. So there is no like two lines of melody. Even if you have some chords, they're happening together. I mean, you can safely kind of remove this chord and don't affect the mean mean melodic idea in the first line. Therefore, I kind of process this data set using this monophonic type of approach. And I just remove the homophonic part, the accompaniment safely, because I think it won't affect the mean progression of the melody. So yeah, I still use PyTorch to train this thing. So for the dataset, so actually this is the dataset I kind of selected, the files. And I didn't select all the files because I also, like I said, right, the BPM was really not kind of unified. So all these files have the similar BPM, like around 80. Okay, so therefore it is safe for me to use the quarter note length to notate those files because they have the same BPM. If one file have BPM of 80, another one have like 120. So if I mix these two files together, because they basically have different BPM, it's like there will be a problem, right? Like what I showed yesterday in the challenge of the time. So for this thing and this thing, so they look kind of very, very similar, but because they have different BPM, they will sound very differently. So this was the problem I considered. Therefore, yeah, I didn't like to select all the files. This is my chosen file, which has the same BPM, and then I process this as note, duration, and the beat level, right? The three information I mentioned yesterday. And then you need to write something to make them one hot vector. Okay, so one hot vector, as I said, only everything 0 except for one position is 1. So this will be your input. For example, the note, yeah, so this will denote some, the MIDI number. The MIDI number, like you need to find these categories and make them one hot vector. Yeah, and every input, like duration is also, one hot vector here. Okay, so, and the structure level, the beat level is also a one hot, I think. Yes, the one hot vector. So there's a little bit of statistics happening here, but after that, I also did a data augmentation, right? Because I only have 10 files. It's too few files to train a neural network. So usually the approach is to do a data augmentation. So traditionally in this image, okay, in this image, they will do this kind of translation. Kind of you move the picture like a little bit left or right or up or down. It won't affect your perception of the objects in the picture, right? So this is what the machine learning, people do like for the image. So in music, it's not like, for this RNN, it's a little bit like image. You cannot make it left, right, up or down, but we can do this key translation. Okay. So if I translate the key, maybe like from C to J or something, then I basically get more of the data files. Okay. So okay, let me see. So there are some notation here, like how I did this key translation. So it's basically just translate the same note to different keys so that I can get more files. So now I have 23 files. And then I just apply those files using my recurrent neural network. Okay. And for this process, these functions, we can get a little bit to them today because I will talk about neural network. But for data processing, these are the basic procedures for me to do for this monophonic, monophonic songs. So for the kind of expressive music, because we talked about, right, how to encode things in this real life time, like seconds, milliseconds, and we talk about this polyphonic, right? The first expressive timing and the polyphony, how do we generate polyphonic music, and how do we process this polyphonic thing? And another is control, right? How do we add this system pedal information to the data processing? So this will be the topic today. Like, let's see how we do this data processing differently. Okay. Okay. Any more questions before I start? Okay. Then let's get into this. So yesterday we talked about the 3 challenges, and today we will just think about like how do we really do the data processing based on these challenges we brought up. So what is expressive music? What is expressivity in music? So let's maybe listen to 2 examples. So this is the first one. Okay. Maybe let me just open them in here so that we can do the score follower. So the first one is the example we used, right? The solo cello monophonic music. You play this. Okay, so this is the kind of called sheet music or staff, music. And when the MIDI player play this music, it's just follow the score, and everything is just exactly as what's presented in the score. Okay, yes, it is beautiful because it's well composed. But in terms of performance, right? So it's a real good music, but the computer didn't give it a performance. They just make this score like audible. So for expressive music, let's listen to this example. So this score looks much more like much more complicated and much more like irregular. But let's listen to this. Seems my player is a little bit slow because we are using the Zoom thing, but you can tell the difference, right? What's the difference? Can anyone share your thoughts like about listening these two 2 different MIDI files? So this file is still like in the format of MIDI files, not really like recorded raw audio or something. It's still encoded as in the MIDI format. Yeah, much more complex. Why? Why is more complex?
The different types of variations applied here, I think.
Okay, yes. So actually more complex. I think it's more like, polyphonic, maybe texture, many notes are having like come together, like many ideas are having together, right? It's not one line, like
No,
one idea happening like all the time. Sorry, what?
number of voices is changeable. So, but maybe is it necessary to um, make a neural network that imitate such kind of polyphony? So I think, for example, I saw in some bars there are different in the left hand, in the part of the left hand. Um, Sometimes there are different voices, different number of voices. So is it necessary? I think it's some kind of um, mm, it's there are no rules about it in the classical music. So it's some kind of human factor, I think. And am I right that we try to make a neural network that has the same human factor? Yes.
Yes, yes, you are right. You are right. So this is not a traditional score. It's not written by human, but it's played by human. Yes. So MIDI file, although we are still dealing with symbolic music, it's not raw audio, but this is actually performed by a human. And when they press the keys on the piano, there was a sensor. Okay, the sensor will kind of notate which key you are pressing, how hard you are pressing that, and on what time you're pressing the key. So this is actually a reflection of a human performance. Okay, so this is what the MIDI file can do. It's not only about excuse me, please.
Okay. Am I right that it's the main aim in front of the programmers who works with the neural networks to make a neural network that uh, imitate human playing most precise? Yes.
Yes,
It's
yes,
okay.
yes.
Or maybe it's not time to ask about it, but it's interesting. Are there some aims that something about uh, unique features of neural networks, about composing unique, maybe some different music that have difference in no, from the human music, from human composing, or maybe it's not your interest.
Well, so what the neural network generates depends on what data set you input, right? So for my experiment here, I input this kind of data because this is the data set I can get. So first you need to get a kind of not small data set if you want to train a neural network work well. Okay, so it's often a problem because for music, right, it's very difficult to get a lot of music, a lot of good music, and also processed music. So the first thing you have to address is that you need to have a data set. So here for this data set, this is also it's something called e-piano computation. Okay, e-piano computation. So okay, let me write this down. Okay, and so on this website, it contains like many years of, because they have this piano competition, and they have real human computers, the performers there, and they play on this Yamaha piano. Okay, for these scopers, and they just use a kind of sensor, as what I said. They just recorded this thing into this symbolic MIDI file. And there is a lot of these files. I think it's at least 200, you know, very long and actually corpuses.
We don't see the site. We see only musical.
Yes, this data set is already taken down. Okay, it was, I don't know why, but I downloaded this like 3 or 4 years ago. For now, if you search it, it wasn't there anymore. I mean, and it's also like, you know, interesting because some people only provide things for a period of time. So for many things, it was there, you know, maybe 2 years ago, but now if you search for this, you just take this down. It's just how everything works. Okay, so I can show you the raw data I got. So some data set for this one, it's here. Yeah, so you can see from 2002 to 2018, and if you open this, it's everything in MIDI file. Okay, and all these are performed by real human. And let's see if we open one of them and just listen carefully. You can see this is MIDI file, right? .MID. Okay, so a little bit slow, you know, for this internet thing. I don't know why.
So basically, this is where you got your data of expressive performances, right?
Yes, yes. So you need to have a source of data set. Yeah. So this music sounds like looks like this. And it's not always the case. Like, I mean, it also depends on your experience. But if you have a data set of your own like performed music, like you're a performer, or you just want to train some neural network that imitates your own style, then you can just do the composition by yourself, right? And then you can write a lot of music that you think is representative of yourself, and you use this file to train the neural network. And if you train it well, the neural network will generate something that, you know, imitates what you inputted or what you kind of feed into it. But because this is a really cumbersome task for people to do, like, I mean, if I can write that many, you know, songs, then I probably don't even need a neural network. So let's listen to this performance. It may not sound that natural because this file, yeah, when we play it in music score, it doesn't contain the control message. Therefore, we have no, like, you know, pedal, system pedal, things like that. So it may sound not that natural, but you can see, yeah, this is a music performed by real human and well composed, you know, piano music. So for symbolic music, where to get the data set, where to get enough data set and the good quality data set is always a problem. I mean, it's also a problem for audio. I mean, you have more. I mean, if you train audio, you have more sources. I mean, you can get the music. I mean, the complexities are different. Okay, for audio, you need more kind of, you know, processing things. I mean, it's different, but because my scope is within this symbolic music field, and then what I would say is that it depends on what type of data set you can get. Okay, so this is the data set I got, and I know, okay, now I have this data set, I can design a system based on this data set, and I can train a neural network. Okay, that's probably kind of can reflect, you know, the property of this data set. Okay. Any questions? Yeah, very good question. Yeah, this is like what we try to address here. And the things I want to show is that also that even if we don't use raw audio, we use symbolic music. We can also generate, this kind of thing, this kind of music that's very expressive. That's that's not inferior to the quality of raw audio. And the good thing of symbolic music is also it's very concise, right? You have the notes, you have, it's much less data, than the audio files. Okay. Okay, let me see what's Sergey. Yeah, it is the different website than what I used to download, but maybe this is workable. Maybe they just transferred their platform. Yeah, I'm not sure. Maybe this is the new website host that they choose, and they still offer this thing for free. So okay, so maybe let's continue with this. So we listen to this, and now because the kind of music score is not really a good reflection of what's happening in the MIDI file, right? Because we have different timing, and this kind of timing are kind of quantized, automatically by music score. It's not a real reflection of what's within this MIDI file. Therefore, we use a more precise representation, which is the piano roll. Okay. This is the piano roll interface in this Audacity. Okay, so if I input the MIDI file into Audacity, this is what you get for the first one. Okay, for this for this one, this solo cello. Oh. Okay, so this is, you can see they have this constant velocity on 100. There's no dynamic change, and all the notes, they are right on the grid, right? So they are on the grid, they are quantized, and these notes are actually monophonic, like one after another, right? There's no simultaneous notes. And this is the piano roll representation of the solo cello. But for this piano performance we just listened to, the piano roll will look like this. Okay. You can see there are more notes and more complex. First of all, this, you can see this velocity. They have a lot of dynamic change along the performance. And also the notes are not quantized. They can be off grid. They can be, on-site, can be any kind of time, not necessarily, right on the grid. And there are also like many like simultaneous notes, right, happening here. Like these chords are happening together, and these notes are also, simultaneous. So, so the question is that how can we process this type of file, right? This type of representation. It must be different from what we did last year, like for this RNN. And also another thing is that what type of neural network we should use. If we continue to use this RNN, like how do we deal with the time, deal with polyphonic structure, and how do we deal with the additional information from the score. And also, for this real human performance, we have this system pedal, okay? The pedal information, this MIDI control message there. So what we noticed for this expressive piano performance, different from the programmed one, okay, this score representation is first is micro timing, right? Micro timing, the music the onside is like more diverse. Now, not necessarily quantized to the grid, polyphonic texture, and varied dynamics, and also pedal effects. Okay, So how do we generate this thing? How do we think about this? So I also asked this yesterday for you all, like we like kind of like, you know, crowd sourced the solutions, right, to this thing. So this is the solution actually I kind of came up with. It's not really has to be the only one, the only solution or the best solution. It's just the solution that I think it might apply to my purpose. Okay, and you can have your way of doing this data processing. You can come up with your own solutions. Yeah, it is everything is fine, but this is the solution that I kind of brought up based on my knowledge and my understanding, whatever. Okay, so first for micro timing, then the thing we do is that we will abandon the fixed grid or quantized duration. So we are not going to you know, go back and say, okay, everything is off grid, and now I'm doing this quantization again, and I'm, you know, reducing the possibilities of onset and duration. So this is not what we will do. We will abandon this fixed grid or quantized duration. We'll use the real time, real onset to mostly capture the micro timing. And to do this, we need to change our time, right? Because previously, when we train the neural network, we use this quarter length of note. Like we just say, okay, this note is 30 seconds. This note is, you know, eighth, half, the whole note, quarter note. But we are not seeing that anymore, because this, you cannot really define a note by, you know, by this type of fixed length or fixed duration. Instead, we'll use the real life time. So we know in MIDI file, there is a way to represent the time using microseconds. Okay, a microseconds is too small for our perception. Therefore, I use milliseconds instead. I think milliseconds are already good enough, you know, to capture this subtle variation in time. And next is for polyphonic texture. So this is more tricky. So first, this is a real human performance, right? So we are based more on these auditory features. The second, and yeah, because it's a human performance, although it kind of follows the real, you know, score that, you know, composer written, but the performance is different. Actually, the timing are different, a little bit different from the score, and there are some, you know, expressivity that the performer kind of endowed to the music. So in terms of polyphonic texture, we are actually approaching this problem more from the performance side, you know. So from the performance side, one thing we notice, one very important thing we notice is that there's no simultaneous onset, right? So in the music score, like what we see maybe previously, right? So when the composer writes it down, there are a lot of, you know, simultaneous on tag for this 1, 2, 3, 4, 5 notes. Sorry. Here on the score, of course, it looks like they happening at the same time. But when the real human perform that, there is always some you know, the subtle difference, time difference between these notes, right? There's no simultaneous time, like exactly same time for two notes to, you know, to be pressed together. For like either milliseconds or microseconds, there is always a little time difference. I see. So yeah, in the chat it's MP3. Okay, MP3. Then you need to deal with this audio file. But actually, okay. So, well, I think we can continue with this this thing maybe later on. Okay, about this data set thing. Okay, so I really want people to understand. I mean, and also do agree with this conclusion. Like there is no simultaneous onset. So this is very important to process this data set, because if we have a system that can deal with, you know, simultaneous nodes, then it is fine. But the problem is that we always don't. We use this recurrent neural network, which is in this sequential fashion. Okay, recurrent neural network is designed like one by one, right? The generation is one after the other, after the other, after the other. So there's no real like parallel system in the recurrent neural network. So if we notice this thing, then it is possible to still represent the music in this sequential or linear manner. Like yeah, so the processing can be still like one line, like monophonic, but you can produce like simultaneous notes. So the notes, the duration will be simultaneously, but the onsets are different. Like yeah, I think, yeah, I hope you understand this concept. Yeah, it's a small thing. I mean, it's not that difficult if I tell you this, but if you don't know this, if you continue, you know, to still approach things from this, you know, 4 or 5 lines, this perspective, then this question, this problem will be very difficult to solve, you know. And then it means we can encode the note onsets using time shift. So with time shift, so okay, because everything here is not, you know, is not quantized, it's not on the grid. The time shift will be, you know, the onset from the first note to the second one, right, to the next one, because we know now we have the order, right? No notes are simultaneously, therefore there is always one note ahead, one note later. Then we can in time sequentially order them. So let's see, like for this note, this is, let's see, this is first and this is the next, this is the next, this is the next. Okay, although there are simultaneous notes, but for this note it happens actually prior than this one. Okay, this is a little bit more earlier. So when we sequential this group, when we sequence, okay, this group of nodes, so they are kind of simultaneous nodes. If we note them in the music score, they will be simultaneously, okay, the polyphonic music. But here in the performance, we can see that actually this is the first one, right? This is the first onset. This is the second. This is the third. This 4, this 5, and 6. Okay, so which means we can sequence them in time and give them, you know, this order number, and then we can use neural network to generate. And this will be the first, and this is the second. You know, we generate this one by one. And with time shift will be we detect all these onsets, and from this time to this time, the time difference will be the time shift. Okay, and from this to here is another time shift, 3 to 4 time shift. The time shift will be the time difference between these two onsets, only the onsets. Okay, it doesn't matter like how long this note lasts, but we only detect the onset as the time shift. And also very dynamics. For dynamics is much easier because dynamics are actually quantized in the MIDI files, like the notes. Okay, it's quantized to 128 discrete numbers. So we will provide how to process the dynamics like more perceptually, more precisely, that reflects our perception. But it is also okay, you know, for you to use the dynamics in this file directly. It's only like 128, you know, different categories. You can use like what's default there. You just leave this multi-processing procedure out. It's fine. So we also need to add this dynamic information into training because, you know, now we have this dynamic information. And also the pedal effects in the control message, we also need to add the pedal, right? I showed you like how it affects this perception of music with and without the pedal. Therefore, we know this pedal information is important. It is significant in determining the performance, the real, the quality, right, of the generated music. Therefore, we need to incorporate the pedal effects into the training. So now let me show you the last one first. Okay, let me show you how to process the pedal effects and how to add this into the neural network. So continue with our notebook yesterday. So this is processing pedal information. Okay. Okay, this is data processing methods. Okay, this is what I just mentioned. It's the same as what I just said. Okay, so time is measured as the absolute perceptual scale in real life. And onset is incremental based, which we use the time shift. And notes are as what's there, right? The notes are discrete because the piano keys are discrete. It has this note range, and we don't need to do more processing for the pitch. Velocity, yeah, can be. So we'll talk about this, how to describe this velocity more perceptually, but you can also use these default numbers, okay, there in the file. And the control number is a steam pedal and a soft pedal. Okay. So this is the file we just listened to, the C piano thing. Yeah, it is the same as this one. Okay, so let's process this file in our notebook. And it's the same thing, okay? We just convert the MIDI to CSV, first of all. Okay, it seems I restarted this package, therefore I need to go back here to run this. Run that first. Yeah, again, I will write my file into this txt text file, and then I write it to this data frame. Okay, then I extract the control message, and you can see the control number, right? What type of control are presented in this file? There is 0, 7 is the volume, 32, yeah, 32 is something like, you know, MIDI control or something. So what we really care that's really kind of affect our perception of the performance is the pedal. So here, the 664 represents the steam pedal. 67 represents soft pedal. So actually, as the steam pedal has more dramatic effects on piano performance, so within the scope of this work, for the data set I get. So I did some experiments. It seems soft pedal only kind of, you know, affects the volume a little bit. So I just decided to discard this information. It is safe. I consider it safe for me to discard this information in this context. But for the steam pedal, it has more dramatic effect on this piano performance. Therefore, I need to add this information into my dataset. Okay. So I call it the sustain control. Okay, CTR is control. Where I get all the control number equals 64, which is the sustain pedal. So let me run this. So now you can see, like, right, all these control number are 64 and different numbers, and everything is control. And then I will do this. So why am I doing this? Because actually for the pedal information, okay, so maybe let me go back to the standard file that illustrates the control message here. Okay. So here you can find all different controls. 0 is band select. What about 32? 32 is some LSB controller. Yeah, MIDI CC. Okay, 64 here. this is what we want for the pedal, okay? For the 16 pedal, and you can see on this illustration, it said its pedal is on or off. It's a switch, okay? And nearly everything will react to 64, and this is if it's lower than 63, it's off. If it's louder than 64, it's on. So in this file, it somehow tells you that for the pedal information, it's a binary choice, either on or off. Okay, on or off. So it gives you this threshold. So lower than 63 is off, upper, higher than 63 is on. So this will be a kind of more convenient way for us to deal with this extra information. Because if we don't do this as a switch on off, then this pedal actually have also 128 different levels of the pedal. But here, for simplicity, we can just compress this information into the binary choice on or off. So this is more simple for us. And therefore here, what I did is to convert so these numbers, so these numbers into on or off. Okay. So actually, I didn't use the threshold as 63 as they wrote here. Okay, I used a lower threshold, which is actually 50. Yeah, so I use 50 as the threshold, which I'm saying that for the number here, okay, from 0 to 49 is off, and 50 to 127 is on. So I use a lower threshold, which means I just take more pedal information in. I think this is a little bit flexible because based on my experiment, and my listening and everything, I think this is a good threshold to use in this data set. Okay, so for data processing, there's also a lot of listening process, like how you perceive this data, and this decides how you will approach the processing, how you will deal with the data set. So I mean, of course, you can use the default threshold like 63, but I just use a lower one. I think it better perceives my perception. Okay. So I use this threshold at 50. So I say, okay, if it's smaller than 50 and the switch is 1, I just change the switch to 0. And if it's larger than 50 and the current switch is 0, I just convert the switch to 1. Okay, so it's I turn it on, off, like this. And after that, okay, PPQ is seems I need to run everything. Here either PPQ. Well, it's not that important because I didn't run everything beforehand. Well, that's okay. Yeah, works now. Yeah, after I processing the 16, I changed this data frame, right, to this one. So now instead of discrete, categories, discrete numbers, I have status. So status tell me this switch is on or off. So off is 0, on is 1, and this is the time. And I also use milliseconds here. Okay, so the milliseconds here. So this gives you the microseconds, as we talked about yesterday. And if you divide 1000, and this is gives you the milliseconds. So for this type of time onset, which means at this time I turn it off, at this time I turn it on, and this time I turn it off again, and this time I turn it on again. And I think this is a good representation of what we saw in this graph, right? So yeah, at some time you turn it on. So here you switch it off and on again, and off, on again, off, right? This is happening like this. So this is how I process the pedal information. And now let's talk about the perceptual processing of the timing. I mean, timing including the onset, right? The onset, duration, and also the dynamics, the velocity. Okay. So here I use this something called male quantization and something called perceptual processing. So if you ever dealt with audio processing or digital audio processing, you might know this thing called male spectrogram or MFCC, right? Male cepstrom coefficients that people use to describe better the frequencies of human perception instead of Fourier transform. So that in that example, they use this male quantization because in this male scale, it's better reflects like human perception. Okay, it's not a mechanical or engineer thing. If for engineers, okay, it's always better to do something like we saw here. Okay, do something like this. These velocity are actually measured by the recorder, and then the pressure, right? The air pressure was like detected by the machine, and this is the representation of the machine perception or the real kind of pressure or amplitude of the wave. But in terms of human perception, there is always a discrepancy between the real kind of physical structure, physical properties, and the perceptual properties. This field is called psychoacoustic. Okay, if you're interested, you can look into the psychoacoustic that describe how you perceive the sound. But here, I tend to use a better kind of scale and processing procedure that reflects this kind of reality, which called the male quantization. What is male quantization and why we use it? Here is a good YouTube video that illustrates this kind of concept, like why we are using this specific scale. Okay, so let me play this for you.
So imagine that we've got your arm here and got these nice.
I don't know why this is always there.
So imagine that we've got your arm here and got these nice big strong muscles, and you're holding in your hand a weight. So let's say that you're holding a 2-pound weight. Okay, so here's a 2-pound weight. And let's say that you're holding it in your hand and you want to lift it up. So as you lift this 2-pound weight, you kind of notice that there's some resistance, and you definitely are able to notice that there's a weight in your hand. So let's say that we took this weight and you didn't know, let's say I grabbed the weight out of your hand and I replaced it with another weight that was 2.05 pounds. So I've got this 2.05 pound weight, and it's the same exact shape and everything, and it's just 0.05 pounds heavier. And let's say that we replaced this guy with the 2.05 pound weight. And let's say that I asked you to lift this new 2.05 pound weight. And you might lift it and you may notice that it's different, but most people in general would not notice any difference. They would just think it's the same exact 2-pound weight. So basically what I'm trying to say is that this 0.05 pound increase in the weight for most people probably would not be noticeable. So let's say that instead of giving you a 2.05 pound weight, let's say that I gave you a weight that was 2.2 pounds. And let's say you close your eyes and I took this 2-pound weight out of your hand and I replaced it with this new 2.2 pound weight. So, and then I asked you to lift the new weight. Most people would probably notice this new increase, this new weight. And so basically what I'm trying to say is that an addition of 0.05 pounds probably wouldn't get noticed, whereas an addition of 0.2 pounds would get noticed. So the threshold at which you're able to notice an increase or a change in weight or really any sensation. So that threshold where you go from not noticing a tiny little change to actually noticing a tiny little change is known as the just noticeable difference. Noticeable difference. So we can abbreviate this as JND. So in this case, the just noticeable difference, let's say for just sake of argument, is 0.2 pounds. 0.2 pounds. Okay. So let's imagine that instead of starting with a 2-pound weight, instead we started with a 5-pound weight. So 5-pound weight. So the 5-pound weight is much heavier than the 2-pound weight. And in this case, if I replace the 5-pound weight with a 5.2-pound weight, because it's a lot heavier and you're using a lot more muscle fibers in order to lift the 5-pound weight, you may not notice the 0.2-pound increase. So whereas if I replace the 5-pound weight with a 5.5-pound weight, so 5.5-pound weight, and I asked you to lift it, you might notice the 0.5 pound increase, but you might not notice the 0.2-pound increase. So basically what's going on here is that since you're using more muscle fibers, you're using more sensory neurons, they're not as sensitive to small increases. They're not as sensitive to the 0.2-pound increase. You need a bigger just noticeable difference in order to actually be mentally aware of the change in weight. So basically when you're holding 5 pounds, let's say for sake of argument, the just noticeable difference is a little bit higher than when you're holding 2 pounds. Now, these numbers were just kind of thrown around, and if you actually did this experimentally, the actual numbers might be different, but the concept generally would remain the same. So in the 5-pound weight category, the just noticeable difference is 0.5 pounds. So from this, we can kind of come up with an equation. So let's just define some variables. So I, or the intensity of the stimulus, is equal to 2 pounds in this case and 5 pounds in this case. And delta I, so delta I, would be the just noticeable difference. So it would be 5.5 pounds minus 5 pounds equals 0.5 pound. So for the 5-pound example, I would be 5 and delta I would be 0.5. And then in the 2-pound example, I would be 2 and delta I would be 0.2. So basically, there's actually a guy back in the day named Weber. So Weber noticed in 1834 that the ratio of the increment threshold, so the ratio of the increment threshold, which is this over here, to the background intensity, which is this over here, so this is the background intensity, is constant. So if we were to take 0.2 divided by 2, and if we were to take 0.5 divided by 5, this ratio is actually equal, and it equals 0.1. And this ratio would be more or less fairly constant for a bunch of different weights. And so that's what Weber's law is. So Weber, in 1834, realized that there was this relationship. So we can write this as an equation. So delta I over I equals K. And so K is a constant for each individual person. There's this particular threshold, and the ratio of the background intensity to the incremental threshold is relatively constant, and that constant is this K value. So this part of the equation over here is known as the Weber fraction. So this works for sensory tactile stimuli like lifting a weight, but it also works for auditory stimuli. So imagine you're in a quiet room. If you're in a quiet room with someone else, you can whisper, you can talk really, really softly and the person can hear you. But if you're at a rock concert, you have to be yelling at the top of your lungs in order for someone next to you to hear you. And that's because the background intensity in a quiet room versus a concert is different. And so the delta I, which is whether you're just whispering or whether you're yelling, is different in accordance with the background intensity. And so that's what the Weber's law is basically saying. So if we take this equation over here, let me just give myself a little bit of space. So if we take this equation, Weber's law, and rearrange it, so we have delta I equals the background intensity times this constant. If we arrange it, we can see that this Weber's law predicts a linear relationship between the incremental threshold, which is this value over here, and the background intensity. In other words, as the background intensity gets bigger, the incremental threshold gets bigger. So if we were to draw a little graph, if we were to draw a graph where the x-axis is the background intensity and the y-axis was the incremental, the difference threshold, what we would see would be this linear relationship. So using the concert example over here, a really, really big background intensity would result in a delta I. So this would be, let's say delta I in this case was how loud you were talking. The delta I would have to be a lot bigger than if you were in a quiet room. So quiet room. And so this law would generally hold true for almost any type of stimulus. And it's a good rule of thumb. It's not exactly, you know, set in stone, but it is kind of how most of your different sensations operate, where if there's a bigger background intensity, you need a bigger difference threshold in order to actually perceive the sensation. And in the real world, sometimes people add a different value. So you've got delta I over I equals K. This is the normal Weber's law. Some people will even add in another constant over here in order to take into account the baseline level of activity that needs to be surpassed in real world situations. So this equation can be modified in order to more accurately represent what goes on in the real world.
Okay, so this is the just noticeable difference and Weber's law. Any thought about this, or anyone like know this before? Yeah, okay.
Oh, I
think,
never heard about it
I think
before,
it's pretty
but
like intuitive, at least, right? Whether you know this before or not, after you watching this demonstration, it's very obvious what this author is talking about. So it just means if you have a small value, then a little bit variation will be very much noticeable. When you have a large value, then you need to, I mean, a little bit, you know, increase or decrease doesn't affect, right, the reality matter. So we will apply this idea into our data processing. So what I did is here. Okay, so this is what I did to the data set. So I'm not going to show you this cumbersome, you know, process of doing this, but the idea is that you do a statistic over the whole data set, and you do some analysis of this, and also I mean the real data set actually also somehow corresponds to the Weber's law we just said, right? For example, this is a duration. So how to divide the duration? So of course, if you are an engineer or you just don't care about this, you just apply a linear, right? Like what people always do, you just apply a linear division. Let's say the lowest kind of duration is of course like 0, right? The largest will be probably like 30 seconds here, right? And how do we, because your computer cannot process continuous, you know, data, right? Your data has to be discrete. So you have to provide these different categories for your computer to predict. Okay, so what duration it is in. So before this, we use the quarter length, right? Then this category will be a quarter length, 15, 30 seconds. We have 10 categories. But here, because we are using this real time, so this is the milliseconds. Okay, this is milliseconds. We use the real time, then we still need to devise a scale to divide our time, right? So if you use a kind of computer or system, and then how do you divide this? Of course, you just divide this, you know, equally, right? You provide this linear scale, equal division. And let's say this is probably like 20 or 50 something, and this is 100 or something. This is 150, oh, this is too small comparing to this number, but fine. So this is the idea, okay? So you provide this kind of linear scale, equal distance, and then you just divide. Then let's say this is my category 1, this is 2, this is 3, and then I just say, okay, if you fall within this this division, I just say, okay, this is category 2. If you fall into this this range, and this is 4, so on and so forth. Okay, but is this really a good scale or a good division to process this time? The answer is no, right? Because we know that when the duration is very small, let's say a node like lasts for 0.2 milliseconds, then if we increase the duration to 0.3 milliseconds, this is very much noticeable. But if a node kind of lasts for 5 seconds and you make it 5.1 seconds, right? You still increase 0.1 seconds, but it's basically the same. I mean, right? You either produce a node 5 seconds or 5.1 seconds. It doesn't make much difference. Therefore, the Weber's law, or this kind of like Mail scale, applies here. Okay, so you can see here, when my duration is very small, this division is very condensed. Okay, but when my duration become larger and larger, this division becomes more sparse, and right, and you can see like when I get to this kind of 15 milliseconds, then I just don't care. Like it lasts 10 seconds or 15 seconds. It doesn't really like matter that much like to me. Yeah, exactly how long. Therefore you have a very large kind of range here. So one thing to notice is that here we don't really use the same scale as was described before, right? In that video, it's described this relationship, right? And if you solve this equation, you will get something of the exponential thing, okay? Something like this, exponential. But our scale is not really exponential, okay? You can see, so this scale is devised by the just noticeable difference, GND, that's the Weber's law, and plus the real statistics. Okay, so you still need to analyze your data set, and based on your own data set, then you can design a scale that best reflects your data. So what scale best reflects the reality of your data? One thumb of rule is that you have same amount of nodes in each duration, in each of this range. Okay, in each of this range, you have similar amount of nodes. Therefore, it prevents like, I mean, if you use linear scale here, maybe in this range, I have 2,000 examples, but in this range, I only have 10 examples. Then there will be a discrepancy also in training, because when we do machine learning, we always want to balance the data set, which can maximize the performance of neural network. Okay, so if you have such difference in these different kind of divisions, then this will be a problem. So the ideal thing is that the number of examples are similar, for these ranges. So let's say maybe I have 200 nodes here, but I also have kind of maybe just 222 nodes here. Then this is a kind of a workable scale, because for my different divisions, for my different categories, we have similar amount of data. Okay, so this is also like addressed a lot in in this data processing for neural networks, the scale problem. Okay, so the same thought applies to time shift. Okay, so in time shift, you can see it is a little bit different kind of division from this thing, from the duration, but the idea, right? The basic idea is similar. When you have a small time shift, the division is more condensed. But when the time shift becomes larger and larger, your tolerance for the difference also become higher. Therefore, you have larger range to divide for this time shift, right? So, for example, like for two nodes happening, 0.1 milliseconds, or 0.1 seconds apart. If we increase to 0.2 seconds, it's very noticeable. But if one node happens at, if the time difference or the time shift between two nodes are like 3 seconds, then I increase this to 3.1 seconds. It doesn't really make much difference. So the last is for velocity, for this dynamics. So for the dynamics, you can also use a kind of Mail scale or nonlinear scale. So normally, people will use just linear scale, right? Equidistance scale to represent velocity, and it works. It works. It's just I feel this may be a better way to do this task. So here it's the same, right? So here 0 is here in the center. Therefore, like when your velocity is near 0, so this is actually a relative velocity. Okay, it's not the number you see. Okay, let me explain this better. Let me go back here. Velocity control. Okay, so here the velocity is 100. Not really good. We want some dynamics. Okay. I want to find some. Okay, so maybe here. Right. So for this piano performance, we have dynamic velocities. Okay. So the scale I use for velocity is not for these absolute values, but the difference between them, right? So when you notice the dynamic change, right, you always compare like the change of the dynamics. Like for example, for now, this node has velocity maybe 69. I care more about like whether the dynamic or the volume increase or decrease instead of the actual number, the absolute number happening there. So to describe the dynamic change among different nodes, then I devised this scale. Okay, so this scale describes the relative velocity. So from the prior node to the next node. Okay, so and I'm just measuring, and maybe it's increase 1 or decrease 2 or increase 5. So usually for two adjacent nodes, the dynamic won't change that much. Okay, if you think about one node like really quiet, the next node really loud, and then quiet, then loud, then this kind of composition doesn't have consistency, right? Usually the dynamic changes, maybe if the volume like increase, this will change like by time, right? Little by little. If something kind of attenuate, it also has a certain time period for it to do it, right? That which means for the adjacent nodes, there won't be much velocity difference between them. Okay. So because there is a gradually happening velocity change, which means when the number is small, like I'm only changing like maybe increase 1, increase 5, increase 6, but it's very rare for me to increase 50, right? it's very rare for me to increase my volume from the first to next note, like 50, 70, like that. Therefore, this is also a kind of perceptually intuitive scale for me to describe the relative change of velocity. Okay, so so this is the data processing kind of procedure I took in doing this work. So I didn't really incorporate the code here. Yeah, if you want to look into the code, I can just briefly show you. But yeah, that would be really messy, and I didn't really organize that. It's difficult to organize. It takes a lot of statistical process for doing that. Okay. Any questions so far? Actually, we already finished the data processing part. Okay. If you have any question, I think we can kind of discuss now. And my next part and the final part will be on neural network and talking about the internal mechanism of neural network, which will also be a little bit maybe difficult. Anyone here ever worked with neural network and know this a little bit background knowledge of neural network here? No. Okay. Then I think this will be a kind of new topic for you. No. Okay. So yeah, in our workshop this year, we have two, right? My workshop is on neural network. I mean, next weekend, Tornik's workshop is also on neural network. So the mechanism will be similar. Yeah, it will be some new topic for you, but it takes time, really to understand how neural network works and how to design this kind of system. So it's more like engineering type of thing. I will introduce later on. So okay, I think we can probably take a break. So for like 12 minutes. So at 9:30, we will come back and we will continue with the next part. Okay. So 9:30 for me, it will be 12 minutes for you like later. Okay, so 12 minutes break. See you later.